Okay, so this is problem 5.52 out of John Taylor's Classical Mechanics. So real quick, this wasn't a problem that I just picked at random. This was actually requested in my Discord chat. So if that's something you'd like to do, I tend to prioritize questions there just because it's more convenient and we all kind of help each other out. So you can join by looking at the link in the description. I have all the information there. So that's where this is coming from. And number two, part of this problem is computational. And while I will show a graph I got, I don't think the main purpose of this is to show you how to code something that will give you your graph. I do have videos like that on this channel, so if you are interested in that, those videos are available. I also don't think that's really what the student who asked was struggling with, so for that reason, I'm going to not really get into that. Another thing to note about this problem is I don't think it's super difficult, but it is very tedious, and if you are not careful with keeping everything together, you can run into a little bit of trouble. Okay. Oh, and also this problem references example 5.5. So 5.5 is right here if you want to look at it in the Taylor textbook. You must have that, but just know that some of these values and ideas I'm getting from here. So that's just something I want to mention. So in general, the process for this is we want to graph a function x of t, which is equal to an infinite series, n equals 0 to infinity, some coefficient a sub n, cosine of n omega t minus delta sub n, where delta sub n is a phase shift. And you may say, okay, well, how do I graph an infinite series? And what we're going to do is not graph an infinite series. Rather, we're going to cut it off at a certain point where we're satisfied with the accuracy of the series. So if you've worked with a Taylor series before, that's also an infinite series. And often what we do is we often have a certain cutoff where we disregard certain terms, certain higher terms. And it's kind of the same idea here once you're satisfied with the accuracy. I believe in the textbook, he did the first three terms. So that's kind of what we'll do based off of his example. But that's what we're going to do. We're going to cut it off at a certain point. Okay, so what is a sub n, this coefficient? So a sub n, there's this really big equation for it, which is omega naught squared minus n squared omega squared plus 4 beta squared n squared omega squared all over fn, and this is square rooted. It's kind of messy, but all well. Okay, so that's a sub n, and based off of what we're given here, so beta is given as 0.1, so we have that. Omega naught is given as 2 pi, so we have that. We're given delta tau, which isn't necessary yet, but it will be, so I'm just going to write that down. That's important. We're given an F max, so a maximum value of 1. And we're given an omega value of 2 pi over tau. So these are just some, maybe I can kind of box these out. Okay. Now, the first thing we're going to do is calculate all our coefficients. And we're going to do so with different taus. And in the example, they have tau equals tau naught, tau is 1.5 tau naught, so on and so forth. So this value of tau, we'll construct a chart similar to this. That value will change depending on which part of the table we're working on. So that's all this. And let's see, what else is there? Oh, well, we don't know what f sub n is, right? We don't know what f sub n is, but thankfully we have an equation to find f sub n. So f sub n, which I think they call a sub n in the textbook, can be found, first off, f sub naught is f max, so that max that was given to us, times delta tau divided by tau. Okay? And so we're going to start with tau equals tau naught, just as an example. Which this ends up being 0.25, which sometimes, like I said, is referred to as a sub n, or a sub naught. It's the first term. A sub n, so any other term, so that's obviously when n equals 0, but for any other term, it's 2 times f max over pi times n, and then we multiply that by sine of pi n times delta tau over tau. So n equals 1, 2, 3, or 4. If we want to find that coefficient, we find it this way. And we have all these values. We know f max, tau, delta tau, and all that is fine. So, okay, we can find f sub n for any term we want. So that's great. We can find a sub n then, capital A sub n. There's one other thing we need to mention here, and that's delta. So delta is our phase shift right here. And we need to know how to calculate that, because as you can see from the subscript, we're going to have a different phase shift for each n value used. So the equation, and this is all in the textbook if you want to look it up, is tangent inverse of 2 times beta times n times omega divided by omega naught squared minus n squared omega squared. Okay. Hopefully I have all these equations down correctly. Okay, so now we can find a sub n, and we can find our phase shift. So that's really how you want to start these problems. And I'm going to do this for one case, but it's so similar for each additional case that it's really not necessary for, I don't think it's necessary for me to really go through and do the other cases, because if you can do one, really all you have to do is change your values that are dependent on your time period, tau. So if you just replace your old tau with your new one, in this case tau equals tau naught, but in other cases it might be 1.5 or 2 tau naught, then you can obtain the same results. So I just wanted to make that clear with what I was doing. Oops, close the parentheses there. Okay, so let's go through this. Let's actually calculate these values. So the initial value of our coefficient is our max times delta tau over tau. Okay. which our max is 1. So this is 1 times 0.25. And remember, in this case, tau equals tau naught, and tau naught is just 1. That's kind of the way that they're going about this. Yeah, the natural period of oscillation, tau naught equal to 1. Okay, so let's go over here. Okay. And with that in mind, this is just divided by 1, so this is obviously 0.25 or 1/4. Okay, so there's our first one. And if we want to find any of the other terms, we can do that using our other equation. A sub n is 2 times f max over pi times n sine of pi n delta tau over tau. Okay. So let's see what we end up getting. We have 2 times 1. So again, this is for n equals 1 now. 2 times f max is 1 over just pi. Sine of, well, that's going to be 0.25 pi over 1, because tau is equal to tau naught, which is 1. And once we do that, we can get our value here. So let's grab my calculator. And that is 0.45015 blah, blah, blah. Okay. So this is our, we'll call it f sub n. Okay. Now we can find a sub 1 for tau equals 1, because we have an equation for that. So it's just going to be what we just found over all of that stuff. So obviously when n equals 1, omega naught minus omega squared, and with tau equal to 1, that's going to be just 0. So this is f sub 1. I should make a note that this is not just f sub n, this is f sub 1 over 4 beta squared n squared omega squared square root. Okay. And when you do that, you get 0.3582, so on and so forth. And by convention, the way that the Taylor did it here was he essentially multiplied the answer by 10 to the 4th. So in our case, this would be 3582. Yeah. Okay, so that is that part. I also need to calculate for n equals 0, so we'll just do that over here. So this is f sub 0. So if we look at our equation, that'll be 0.25 over omega naught squared minus 0 squared. So this is really the square root of omega to the 4th. Plus, that's all 0. And when I did that and I did their little multiplication they like to do, I got 63. So that's when n equals 0. Sorry, I forgot that one there. Let's say times 10 to the 4th. Okay. That's just the convention that they like to do. Anyways, so that is how you calculate this. And then let's get this here. You would essentially follow the exact same process for what this for what the question asks. So you would just have a table with, say, tau. Let's do it like this. You would have A0, A1, A2, A3, A4, A5. And then you would have tau equals tau naught, tau equals 1.5 tau naught, tau equals 2 tau naught, and tau equals 2.5 tau naught. And not very straight lines, but it's okay. So we found this was, 63. And then we found this was 3582. Okay. And if you continued, you should get 27,501. Okay. And you can do this with the other taus as well. Let's see. So again, you follow the same process to get these 4 values that we used to find A1. The only difference is this F sub n. Obviously your n value changes, so you want to account for that. And F sub n is calculated right here. So that's kind of confusing, the different notation. It kind of confused me earlier. So you can do that. And then you'll be able to get this first bit right here. Let's kind of separate them a little bit. Okay. Now, for the next, section here, tau naught is now 1.5. So what that means is, when you calculate your coefficient, well, first off, your omega is 2 pi over tau, and tau equals 1.5 tau naught. So your omega changes. You need to keep that in mind. The other thing that changes is your coefficients here, because your tau changes. But really, all that needs to be done is you're plugging in a different value than what we were plugging in before. So I'm just going to fill out this chart. 42, 145, 90, 18, 6, 2. And I'm going to kind of stop there, but it's the same process. It's pretty repetitive for the most part. You just have to be careful and know when to change what values. So that's good, but now we have to find our delta values. So the way that the book did it is, once they actually graphed x of t, if you remember, x of t is this infinite series. This infinite series, and the book seemed pretty content with just taking the first 3 terms. So I'm going to expand this. Obviously, n of 0, you're just going to get minus delta n plus a1 cosine of omega t minus delta 1. That should be naught. Plus a2 cosine of 2 omega t minus delta 2. Was there a pi in here? I guess it's in the omega. Yeah, okay. Well, this is that expanded infinite series. Obviously, there's more terms, but what we're saying is, it's okay. We're getting a perfectly fine approximation this way. Okay, and we calculated these. So we can say for tau equals tau naught, you can just look up here. We have a naught, a1, a2. So that's not a problem. There is delta. So again, we have an equation to calculate delta. Delta is tangent inverse of 2 beta n omega, all divided by omega naught squared minus n squared omega squared. Okay. So we can calculate our deltas this way. For n equals 0, obviously, so delta sub 0 is tangent inverse. And then, see, this is just 0 over omega squared. Okay. So that's obviously 0. Not much to say there. And we can do the same thing with all the other terms. Again, we're not going to calculate every delta because we only really need the first couple. And I think this was the one I wanted to talk about, because this one's a little weird because it appears that we're going to have a little bit of an issue here where omega naught is omega. So it looks like we have a domain problem. But it's important to remember what tangent is. Tangent is sine over cosine. And tan inverse is essentially spitting back out the angle for a given argument. So the question really is, where is cosine 0? Because that makes tangent undefined. And of course that happens at pi over 2. So this is delta 1. And then delta 2, again, you'll calculate the same way. Okay, so you have all of these. Now what we can do is we can graph this. And so we can plug in for our A naught. We can plug in for our deltas and our A's. And we can just put this in any old graphing calculator, which I'm going to do here in a second because I just have my phone. So I'm going to kind of snip videos together here. So here you can see the graph that I just put on Desmos really quick, where I graphed the functions and I plugged in the values that we found earlier. And keep in mind that those A naughts were times 10 to the negative 4th, so our graph kind of looks like this. And I also wanted to just show you what I put down here in the system to get this graph. So hopefully this helps out, and if it did, please like and subscribe. Thank you, and I'll be posting more soon.